We now continue our discussion, and let's have the factor theorem. The factor theorem allows us to easily check whether a polynomial has a factor of the form x minus c. As the remainder theorem points out, that if you divide a polynomial p of x by a factor x minus c of that polynomial, then you will get a zero remainder. Example, we determine whether x plus 2 is a factor of p of x equals 3x raised to 4 plus 5x cubed minus x squared plus x minus 2. So first, we are to equate x plus 2 to 0. So x plus 2 equals 0. We now isolate our x, therefore x is equal to negative 2, which is our c. We are going to substitute negative 2 to all x in our p of x, which is equal to 3x raised to 4 plus 5x cubed minus x squared plus x minus 2. Copy p of x equals 3x raised to 4 plus 5x cubed minus x squared plus x minus 2. We now solve for p of negative 2, which is equal to 3 times negative 2 raised to the power of 4 plus 5 times negative 2 raised to the power of 3 minus the square of negative 2 plus negative 2 minus 2. 3 times negative 2 raised to the power of 4 is equal to positive 48. 5 times negative 2 raised to the power of 3 is equal to negative 40. Negative of the square of negative 2 is equal to negative 4. We simplify plus negative 2, and that is written as negative 2. Then we copy minus 2. 48 minus 40 is equal to positive 8. Positive 8 minus 4 is equal to positive 4. Positive 4 minus 2 is equal to 2. 2 minus 2 is 0. P of negative 2 is equal to 0. We can now say that x plus 2 is a factor of 3x raised to 4 plus 5x cubed minus x squared plus x minus 2. Next example, we determine whether x minus 1 is a factor of p of x equals x raised to the power of 25 minus 1. We equate our divisor, which is x minus 1, to 0. Then we now solve for x. We transpose negative 1 to the right side of the equation. So x is equal to positive 1. We are going to substitute 1 to all x in p of x, which is equal to x raised to the power of 25 minus 1. We now copy our p of x equals x raised to the power of 25 minus 1. And we are now ready to solve for p of positive 1, which is equal to 1 raised to the power of 25 minus 1. 1 raised to the power of 25 is equal to 1. Then we copy minus 1. 1 minus 1 is equal to 0. With that, we can already conclude that x minus 1 is a factor of x raised to the power of 25 minus 1. For our last example, we are going to determine whether x plus 1 is a factor of p of x equals x raised to 6 plus the product of 2x and the difference of x and 1 minus 4. We now equate x plus 1 to 0. And we now solve for the value of x. We transpose positive 1 to the right side of the equation. Therefore, x is equal to negative 1. We are going to substitute negative 1 to all x in p of x equals x raised to 6 plus the product of 2x and the difference of x and 1 minus 4. We copy p of x equals x raised to 6 plus 2x times the difference of x and 1, then minus 4. We solve for p of negative 1. That is equal to negative 1 raised to the power of 6 plus 2 times negative 1 times the difference of negative 1 and 1, then minus 4. Negative 1 raised to the power of 6 is equal to positive 1. Next, we are going to combine first negative 1 and negative 1, which is equal to negative 2 times 2 is negative 4 times negative 1 is equal to positive 4. Then we copy minus 4. 1 plus 4 is equal to 5. 5 minus 4 is equal to 1. So p of negative 1 is equal to 1. Since our remainder is not 0, we can now say that x plus 1 is not a factor of p of x equals x raised to 6 plus 2x times the difference of x and 1, then minus 4. If your question is, how to find a missing value of the dividend to make the divisor be its factor, then you have to listen to the following examples. Find k so that x plus 3 is a factor of p of x equals x cubed minus 2x squared minus kx plus 12. Using the factor theorem, if x plus 3 is a factor of p of x, then p of negative 3 is equal to 0. Our p of x is equal to x cubed minus 2x squared minus kx plus 12. And take note, our x is negative 3. That's why we have here p of negative 3. This will now be replaced by 0. 0 is now equal to the cube of negative 3 minus 2 times the square of negative 3 minus k times negative 3 plus 12. The cube of negative 3 is equal to negative 27. Negative 2 times the square of negative 3 is equal to negative 18. Negative k times negative 3 is equal to positive 3k. Then we copy plus 12. Negative 27 minus 18 is equal to negative 45. Negative 45 plus 12 is equal to negative 33. Then we copy plus 3k. I will now transpose negative 33 to the left side of the equation. So I prefer to transpose negative 33 because our 3k is already positive on the right side of the equation. After this, I'll be using the symmetric property of equality. So our equation is now written as 33 equals 3k. We now divide both sides by 3. 3k divided by 3 is equal to k. We copy our equal sign. 33 divided by 3 is equal to 11. So x plus 3 is a factor of x cubed minus 2x squared minus kx plus 12 if k is equal to 11. And for our last example, we are going to find k so that x minus 2 is a factor of p of x, which is equal to x cubed minus kx squared minus 4x plus 20. Using the factor theorem, if x minus 2 is a factor of p of x, then p of 2 is equal to 0. P of x is equal to x cubed minus kx squared minus 4x plus 20. And all x here will be replaced by positive 2. P of 2 will now be changed to 0. So our equation is now written as 0 equals the cube of 2 minus k times the square of 2 minus 4 times positive 2 plus 20. The cube of 2 is equal to positive 8. Negative k times the square of 2 is equal to negative 4k. Negative 4 times 2 is equal to negative 8. Then we copy plus 20. 8 minus 8 is equal to 0. 0 plus 20 is equal to 20. Then we copy negative 4x. Since 4k is negative, then it will be the term that we are going to transpose. So our equation is written as positive 4k equals positive 20. We now divide both sides by 4. So k is equal to positive 5. X minus 2 is a factor of x cubed minus kx squared minus 4x plus 20 if the value of k is equal to 5.